Welcome everybody to my talk called Taking Static Type Safety to the Next Level, Physical Units from Matrices. My name is Daniel Withopf. I work at the German car supplier Bosch, mainly on automated driving, so self-driving vehicles and driver assistance. So what's in it for you today? We'll be mainly talking about physical units in vectors and matrices. I think they swallowed the second half of my talk title outside, so I hope you're here to hear about physical units in vectors and matrices. But don't worry, even if this is not interesting for you, there's a lot you can learn today about static type safety in C++ and library interface design. We will learn how we can achieve what I consider the ultimate goal in C++ library interface design, which is given by this one sentence: if it compiles, it works. So what do I mean when I say if it compiles, it works? Throughout the talk, we'll follow a few design principles. First of all, we try to anticipate problematic usages and prevent them at compile time wherever possible. This will go so far that it almost feels like a static analyzer built into your C++ compiler. So it's effectively your math and physics teacher in the C++ type system. Furthermore, we'll try to enable users to make sweeping changes to their code that work once they compile again. And last but not least, we'll try to make user code as expressive as possible. That means ideally you should be able to tell from a single line of code what is going on in that code line without having to have any background knowledge. By the way, it'll be an interactive talk, so I have a few questions during the talk for you. If you have questions, feel free to ask them right away. I'll try to answer them. So before we start off, a little bit about terminology. So in case you don't know much about physical units or physical units in C++, it's fairly easy. You can simply think of them as strong C++ types that behave exactly as you would expect from physical units. So for example, you can add two physical quantities with a unit of meters. You cannot add meters to seconds. And you can also multiply any two physical units together. So for example, multiplying meters with seconds gives the valid result, meters per second. In case you want to know more about this, there is the library by Matthias Pusch and proposal P1935 that he wrote, which is a physical units library for the next C++. So hopefully it will make its way into C++ 26 if we're lucky. Please check out any of his talks, so they're really nice. And you can also check the GitHub link or the paper if you want to know more. But for today, as I mentioned, you don't need to know much about the details. So coming to terminology in linear algebra and in my library, so in classical linear algebra, you usually have vectors, that would be anything that's n by 1 dimensional, and matrices, that's anything that's really 2-dimensional. In classical math, the terminology is a little bit different. So in classical math, you have points in a vector space. There are displacement vectors, which is the connection between 2 points in that vector space. And we also have different matrix types, for example, Jacobians, covariance matrices, and a few others that we will see later. In my library, type-safe matrix, I also distinguish between points in the mathematical sense. They get a vector tag, and displacement vectors get a delta vector tag. This will later on come handy when we want to do strong type-safe checks. Wait a second. We've settled. Good. Now moving on to our actual task. So as I said, we want to combine linear algebra libraries and physical units libraries. So as I mentioned, for physical units, there's, for example, P1935. There's an older library, Boost Units. We also have an in-house library. So there are lots of physical units libraries for scalars. And there are also lots of pre-existing linear algebra libraries, like, for example, Eigen. Or there is also the proposal P1385. Guy Davison is actually at the conference. He co-authored it with Bob Stiegel. Now the question is, how can we use these two? I want to show a small code example. So the first line here is from the physical units library. So here we declare a physical quantity with a dimension of length, and the underlying unit is meter. And then we can create the variable in that way. And the second code line here is an example how we can create a vector from that linear algebra library proposal I mentioned with an underlying scalar type of double. So here we simply initialize the 3 elements with 1, 2, 3, and we have a 3-dimensional vector. Now, first question for you. Does anybody have an idea how we could combine the 2 libraries? So if you want to have a vector that stores physical units? Yeah?
Well, you would simply replace double with an SI length.
Yes, you would replace double with an SI length. Perfect. So we could use the value type to store meters in this example here. That would look like this here. Perfect introduction. So we have an fs vector. It stores the length. We have two of these vectors, u and v. And we can now add these 2 together because they have the exact same physical unit. Both have a physical unit of meters, meaning we can add them together and get a valid result. That's really easy. But now, let's move on to a slightly more complex example. So in my application, for example, we want to track a vehicle, another vehicle that's driving close to us. And for this simple example, we'll just do it in 1 dimension. So let's assume we want to track the vehicle that has a distance in meters, velocity in meters per second, and an acceleration in meters per second square. Then we can simply create such an fs vector here on the right-hand side. We are assigning 1 meters, 2 meters per second, and 3 meters per second square to the individual entries in that vector. Now, what should be the value type here? Is this possible? Yeah. The answer was replacing it with double would be possible? A tuple, yeah. Yes, so tuple is one option that would actually, the next question already, which C++ data type could be used to represent this. So tuple is the first answer. Is there a second option that we could do?
All of them, or one, either a meter or something, velocity or acceleration, because it would be variant.
Yeah, variant is also another option, yes. So these 2 data types could be used to represent them, but I don't think it's a good idea in general. So it might get you somewhere, but with variant, you would have to visit each element, which is tedious. And with tuple, we'll see on the next slide, it also would be fairly complex. So here, that was the answer, tuple or variant. Let's look at a bigger matrix as an example. So here we have a covariance matrix with 4 by 4 elements. And in such a matrix, we would have up to 16 different physical units in each of the elements. And this is a fairly small matrix. We could have 10 by 10, 20 by 20 matrices, which would mean 400 entries for a 20 by 20 matrix. I don't think we really want to represent that with a tuple. I think the compile time would probably explode. Fortunately, the unit structure in such a matrix is a little bit simpler than this, because we don't have 16 independent elements. We only have 4 independent row units and 4 independent column units. And then the individual units of the elements are given by a combination of the respective row unit and the respective column unit. So it's always this case, whenever you have multipliable matrices, the unit structure looks exactly like this. There's actually a book back from the 90s by George W. Hart, where he explained the background. I only found that after I was finished with my work on the topic. But it seems to be that all meaningful matrices have this structure. And this means we don't need a tuple here. We just have to represent the row and the column unit. So in an m by n matrix, we would have m plus n independent units that influence the content. Second. Now I also want to explain a little bit about my motivation or the background where I started off. So in our application, we often have a linear algebra code. Code line might look like this here, where we have an other vector. We exit it at index 3, and then we assign it to measurement vector at index 2. Now, I'm not sure if you have any clue what this code is doing. It was the same for me. I have no clue what this is doing because there are 2 questions that need to be answered. First of all, what do the vector entries describe? Because we have no idea what's at index 3 in other vector and index 2 in measurement vector. Furthermore, this could even be an out-of-bounds access, especially if these are not compile time indices, but even then at compile time it could be out of bounds. Then maybe the user rewrote the code and tried to make it a little bit better, a little bit more expressive. And now we have code like this. So we're accessing other vector at position x index and assigning it to measurement vector at velocity x index. Now again, I have two questions for that code. First of all, have the right index constants for the respective vectors been used? Because there's no guarantee that position x is actually meant for other vector and velocity x is meant for measurement vector. These are probably enumerator constants, but we have no guarantee that they're actually meant for these types. And second of all, this is where your physics teacher comes into play, is assigning a position to a velocity really something that you want to do? Most likely, this is a bug waiting to happen and an incorrect operation. Last but not least, maybe the code line is further improved and looks like this here. So now we're reading from other vector at velocity x index and assigning to measurement vector at velocity x index. Now this looks okay from physical units perspective, but there's still one last question remaining. Namely, in which coordinate frame are measurement vector and other vector? Because if one is in coordinate frame A and the other one in coordinate frame B, and they don't coincide, then again, this is most likely an incorrect operation. From that, I came up with my linear algebra library wish list, so what I would like to have ideally from a linear algebra library. First of all, I would like to have a protection against out-of-bounds accesses at compile time, of course, not at runtime. I would like to have expressive and enforced names for all vector and matrix entries, meaning it should no longer be possible to just take an element 2 of a vector. You should always have to mention what's the content of that index. Then I would also like to have support for non-uniform physical units in vectors and matrices. As we've seen, that approach of using the value type does work, but only if we have a single unit in all entries, so the identical unit in all entries. And I would also like to have a physical units check for all matrix operations, again, ideally at compile time. We will also see later that we can achieve a much, much stronger condition than just physical units safety. And last but not least, I would also like to have coordinate frame annotations for all vectors, for matrices, and also for transformation between different vector spaces, so that you always know, okay, I have a vector in coordinate frame A, this is a vector in coordinate frame B, and transformation goes from coordinate frame A to B, and then you end up with a vector in the new coordinate frame B. Good, that was the introduction and motivation so far, and now I want to move over to the actual solution space. Any questions already? Okay, I didn't explain that much, so questions should come later. Then let's see how we implement that. So the first ingredient for the secret source we need is what I call named index structs. So these are basically tag types, empty structs, that identify each entry in a vector matrix with a unique name. In this case here, we have a distance x, so dxc stands for distance x, Cartesian, and such an index struct is created by deriving from a base class, and we have to specify in which coordinate frame we are. We have to specify that this is the Cartesian x-axis in that frame, and we specify the physical unit of that index. Down at the bottom, you can also see how these coordinate frames are created. So again, almost an empty struct. We just derive from a base class. We specify that the position unit is meters for that coordinate frame, and we also specify whether the frame moves with respect to the Earth. So I'm assuming Earth is fixed, and anything that moves with respect to that would get a moving flag here. We need that later when we transform between different coordinate frames. Now, second example, this here is a y position in a sensor frame, dy sensor. Again, we derive from the base class. We list the template arguments, so fairly easy. And the general rule how I constructed these indices is given here on the right-hand side. So these names consist of 3 parts. The first one describes the physical quantity, is this distant velocity acceleration, for example. Second part describes the axis, x, y, z axis. And the last one describes the coordinate frame we are talking about. So in this example, it's the sensor frame. And I should also mention why that dx frame does not contain a mention of the coordinate frame. In our application, this vehicle front axle frame was the standard frame. So I left out the frame name in that case. That was convention to make it as short as possible. But of course, as these are just structs, empty index structs, The user can create any names he likes, so you could pick completely different names, 3-letter acronyms, whatever you want. That's up to the user. Now let's move on to the first type in the library that I wrote, actually. It's called, as the library, type-safe matrix. And that class has 4 template arguments. The first one is the scalar type, so do we want to represent the matrix with float or double? The second argument is a row index list. It's a type list that contains these indices that we've seen on the previous slide. A column index list that contains the column indices. And last but not least, we have to specify a matrix tag. And that matrix tag is used to distinguish between, as I mentioned, points, proper vectors, between covariance matrices, Jacobian matrices, and a few other types that we will see later on. And this is one of the main influences of the allowed operations. We will see later on that only a very small subset of the possible operations are actually mathematically meaningful. And for that, we need the matrix tag. Now, the only member here in that class is an eigenmatrix, or whatever you want to have underneath. You could also pick a different linear algebra library. And we take an eigenmatrix with a given scalar type, and we take the size of the row and column index list as the size of the matrix. Fairly easy. Now we can create our first alias. That here would be a type-safe vector. And the type-safe vector is just a type-safe matrix with a given scalar type, the given row index list. And as columns, we use sort of an empty type. I call it no index type. This is simply a type that does not influence the physical unit, because in a vector, the column doesn't have a unit. So, but I needed an index for the column, so I use here sort of the empty type as the column unit. And then, last but not least, we can create such an alias here that would be a position vector in vehicle frame of dimension 3. We instantiate that from the template, type-safe vector template or alias that we have here. We list the 3 indices, that's dx, dy, and dz, so x, y, z position. And we give it a vector tag, which means in this case, so we have to be careful, it's a little bit misleading, the vector tag. Maybe this is a point in the mathematical sense. As I explained earlier, if that would have a delta vector tag, then it would be a delta or displacement vector, so proper vector in the mathematical sense. Now let's see how we can create such a vector and how we can access its elements. When we create a vector, we have to list all the elements in the vector. And there are 3 different options how we can list these elements. They're listed in decreasing order of type safety. So the first and most type-safe one is to use the entry method. We specify we want to extract the dx index from other position here. And this only works, of course, if other position also has that entry. Otherwise, the user would get a static assertion. So this means, in this case, there's a full check. The other vector has to have the exact same type. It has to have this entry, and only then is this call valid. So this is the 3-star type-safe version. The 2-star, a little bit less type-safe version, would be to use the rep coefficient SI method. And there you specify the index you want to construct and also the physical unit. So in this case, meters. So we want to input 1 meter for the Y position. And the last and least type-safe option is to use rep coefficient, where we simply pass a scalar. So this is not really type-safe. So this should be avoided if possible. Maybe if you want to set an element to 0 or to 1, it makes sense, but otherwise it should be avoided, and only the first and second one should be used. And similarly, if we constructed the vector, we can also read and write entries or elements later on. So in this example here, we are again extracting the dx index from other position, and we're then assigning it to the respective index in position vehicle. So please note that I don't even have to mention an index for assign entry, because it's clear from the entry method. The return type contains the information which index this is. So assign entry immediately knows that this is the x index. And again, we have a full check. So if dx would not be part of other position or of position vehicle, where we're assigning it to, the user gets a static assertion and can fix the problem. Second option, that's a little bit less type-safe, again, 2-star version only. You can read with coefficient SI from an entry in a vector. This returns the physical unit, and then you can assign with coefficient SI ref to another index. And here we already see we can read from the y position index and assign it to the x position in sensor frame, so in a completely different frame. This is possible here because this only checks the physical unit. Now you might wonder why the two methods are named differently. The reason for this is that I'm not actually storing physical units inside the vector or matrix. I'm just giving the expression on the impression on at the user interface, which means I have to return a proxy type for that assignment here and can't directly return the type. And again, we have the last and least type safe option. We can use the add method for reading and writing. And here it's possible to assign the y position in sensor frame, or sorry, y velocity, in this case even, to the x position in vehicle frame, which is clearly incorrect operation, or most likely. So again, this should be avoided if possible. We can also do a little bit more complex constructions. So in this example, we're creating a three-dimensional displacement vector. And we do that by listing the first two elements here. So we're extracting the first two elements from a velocity vector, from other velocity vector in sensor frame. And then we multiply it with the duration in seconds. And the duration multiplied with the velocity gives you a displacement vector. So that means we have a two-dimensional displacement vector, and we can use that to initialize the first two elements of the vector we're constructing. And then we also have to list the third element. We're doing that manually here by calling the entry method. Of course, this also generalizes to two dimensions. So we've only seen vectors now. This here is a type-safe matrix, so a covariance matrix that contains x, position, and velocity as both rows and columns. And when we construct such a matrix, we of course have to list row and column index for all of the methods that I mentioned earlier. So in this example, we're using the rep coefficient SI method, and you have to list them in row major order. So the order is also checked. If you mix up the order here or mix up the indices, again, you get a static assertion. Then there are also more complex operations that you can do. You can construct a matrix from 4 columns or n columns, from n rows, from 4 smaller blocks, or from 3 rows and 3 small blocks in the last row. Now the syntax here might seem a little bit verbose. This is a little bit tainted by my application, I guess, because I wanted to make everything explicit. But there's also another reason why this is really, really valuable. Because what I did in our application, so we're doing object tracking, you often have vectors and matrices with 10, 15 entries. And at one time, I exchanged the order of all the indices in the vectors or matrices. And when I did that, the library throws hundreds of static assertions at you. Then you fix all the static assertions. And once it compiles again, it works. So there was no bug left over because everything is checked at compile time. So there's no potential for bugs there. So I think this is, again, a nice example for the slogan from the beginning. If it compiles, it works. Now I want to show how we can determine the physical unit of an entry in such a vector matrix. So the code on the left-hand side is a lot. Maybe you can also just look at the visualization on the right-hand side. So this constructs a Jacobian matrix here. And the individual entries are mesh dr, so radial distance to a target from a radar sensor, for example, in unit meters. The second row describes the radial velocity, mesh vr, with unit meters per second. And the last row describes the angle with a physical unit of radian. The 3 columns are fairly easy. That's x, y, and z position in vehicle frame. And now the question for you, maybe you can answer that. What should be the physical unit that should be returned when we call this method here? So we're accessing the Jacobian at the row index mesh vr that has a unit of meters per second, and the column dy that has a physical unit of meters. So what should be the physical unit of that entry? Does anybody have an idea? I can also give a small hint. Jacobians are derivatives, sort of. So you can approximate them with a finite difference quotient that might give a hint what the physical unit should be. If not, just guess something, combine the two. Meter square per second, almost. Second over meter square. 1 over second, yes. So yeah, you have to know which, like the derivative of what with respect to what. So it's the derivative of the row with respect to the column. And I said you can approximate it with a difference quotient, the derivative. So you divide the row unit by the column unit. And there's actually a general rule that applies for all different matrices if we introduce the notion of a row exponent and a column exponent. So for Jacobian, the row exponent would be 1, and the column exponent would be -1. And then the general rule for the physical unit in such an element is given here on the bottom right. So we're taking the row unit, meters per second, raise it to the power of the row exponent, 1, and then we multiply it with the column unit, meters raised to the power of the column exponent, which is -1, meaning we end up with a division of meters per second divided by meter, and we get 1 divided by second, or hertz. Now, this is the full taxonomy of all vector or matrix types, or at least all the ones that I could find. So first group are proper matrices. So there are covariance matrices, Jacobian matrices, information matrices. These are the inverses of covariance matrices. And you can also see the respective row and column exponents. So for the information matrix, it's fairly obvious. It's the inverse of the covariance, sign inverse. Then we have different vector types. So we have a position vector, displacement vector, and information vector. And we also have what I call vector collections. So these are sort of matrices, but semantically the content of that matrix is a collection of n column vectors or displacement vectors, whatever. That's also something that you need fairly often. And that means with that we have a semantic way to distinguish between a real matrix and between column or row vectors stored inside a matrix. This is something completely different from the mathematical point of view. And of course, there are also the transposed version of all of these types, so it should be obvious what the row and column exponents are then, just have to exchange them. For covariance, for example, there's no change, so the transpose of a covariance is again a covariance, and they are also usually symmetric by design. Good. Until now, we've achieved unit-safe element access and out-of-bounds protection. Now the question is, can we maybe do even more? And as we will see, there's a lot more that we can achieve. So first of all, let's try to be unit-safe for all operations and on vectors and matrices. Again, questions on this slide. So first of all, the question, should this operation here be allowed? So we have a vector with x and y position with a physical unit of meter. And we're adding a second vector that contains x and y velocity with a physical unit of meters per second. Should this be a valid operation? No, yeah, I think the consensus is no, because the physical units do not match up, so you can't add meters to meters per second. That was easy. Now, a little bit more difficult. Should this here be allowed? So if we have a point with a dimension of meters, and to that we add a displacement vector that also has a physical unit of meters. Should this be allowed? Consensus seems to be yes. Anybody, other opinions? The world is complex, so.
What are we, have a delta there.
Yeah, there's a delta.
Then you're fine.
Yeah, it seems to be fine. It's also fine in general, but not in all cases. That was a little bit of a trick question. So what if the first vector contains x and y position in vehicle frame, and the second vector is a displacement vector, but with y and z indices in the same frame? Then these two vectors describe completely different things, and it should not be possible to add them together. So this is sort of the conclusion that we should take home from here. The index types do not match up. And the conclusion is that unit safety is not enough. We actually want index type safety in our linear algebra operations. Sorry? Coordinate frames. What about coordinate frames? Yeah. So in the indices also describe in which coordinate frames they are. So if the indices are different, or if it's the same index, like x position in vehicle frame and x position in center frame, that's also different indices. So that's sort of subsumed with that condition. So you also cannot add the same the same x from different frames because it's a different index. And again, I think this is a nice example of If it compiles, it works. Now I want to move on to a little bit more complex operation inside the library. So here in this example, we're trying to multiply three matrices together. So we have the covariance and vehicle frame in the middle, and we're multiplying it with a Jacobian from the left-hand side and a Jacobian transposed on the right-hand side to get to a covariance in sensor frame. Now on the bottom, we also have the visualization of that. So let me see here. In the middle, we have the covariance with the row indices. Here we have the Jacobian transposed, and on the left-hand side, we have the Jacobian. Now let's see what's happening when we multiply these two matrices. So first of all, the first check that the library does is that the column and row indices in the orange boxes are actually identical. This is the first condition that has to be satisfied. And furthermore, the row and column exponents in the orange boxes also have to be the sign inverse of each other, which means that the physical units are effectively canceling out. They have inverse exponents and the same indices, meaning they cancel out. And we end up with the column units from the right-hand side that are now, in the visualization here, moving over to the covariance in the middle. And now the same operation is done on the left-hand side. So we're again checking that the indices in the orange boxes match up and that the exponents are the sign inverse of each other. And if this is the case, again, the indices cancel out and we end up with a row indices from the left-hand side Jacobian that is now being moved over to the middle in the covariance. And now we can already see that we end up with a covariance in sensor frame. So all the indices are in sensor frame now. At the top here, I ran out of space, so these y and vx indices are also in sensor frame. And that's also the value that we're assigning to here on the left-hand side of our equation. So we're assigning that to covariance in sensor frame, and that's exactly the result that we have here. So everything is checked by the library, and this is a valid operation. And if any of these conditions would not be satisfied, of course, the user gets again a static assertion. Now I want to move on a little bit into the implementation details of the library. This is an example of what the addition operator looks like in the library. So here we are accepting anything that's derived from matrix base. So this is the base class for all vectors and matrices and matrix expressions. And the return type is then a matrix expression. And that matrix expression consists of two parts. So the first type is a promotion that is responsible for promoting the types of type-safe matrix. So it tells you what should be the resulting type of the matrix of this operation. And the second part is simply the underlying linear algebra library's expression. So here we're using the Deckel type of the two addition of the two underlying types. So that means we're using forwarding to Eigen here, and this returns an Eigen expression that is responsible for doing calculations at runtime. So this means we have two parts. The first part is compile time information or propagation in my library, and the second part is simply the runtime calculation that's forwarded to Eigen. Now let's see what such a promotion to the addition looks like. This is, again, an almost empty struct that inherits from a few requires base classes, sort of. I should mention that will be important later on. The library has been designed for C++11. I'll explain later what that means. So that promotion to the addition here inherits from requires identical scalar type, and that base class does exactly what it says. So it checks that the scalar type of the two arguments is identical. If it's not identical, a static assertion is fired. Furthermore, this also injects the scalar type into our resulting promotion. So we require both scalar types to be identical. So this base class can then also inject the resulting scalar type. Then we require identical row and column units. Indices, not units. And these two base classes also inject the resulting row index list type and the column index list type. Then we also require identical row and column unit exponents. And last but not least, we require that the matrix tags are addition compatible. That's what I explained earlier. So in classical math, you cannot add 2 points together. That's an invalid operation. But you can add a point and a displacement vector that gives you another point. Or you can add 2 displacement vectors together. So that's basically the concatenation of the 2 vectors. And last but not least, I also want to show what such a requires base class looks like. So requires identical row indices here is, again, almost empty. It simply checks that two types are identical, namely the row index list of both arguments. And as you can see, it checks the row index list of the result. Now, why did I do it exactly in that way? Of course, I wanted to have nice compiler error messages, or at least as nice as they can get with templates. So we'll have a look at an example here. This is an operation where we add a three-dimensional point to a two-dimensional displacement vector. And then, when this happens, the user gets a static assertion first, and that's simply static assertion from the type identity checker that says, okay, two types are not matching. And if we want to get more information on that, we look at the instantiation history, and we can see, okay, this comes from the 2D addition promotion that we've seen, so it happened while we're adding something. Then it happened in the requires identical row indices base class, meaning the row indices of the two arguments are not identical. And last but not least, the type identity checker template is instantiated. And we see, okay, there are two type lists. One has 3 elements and the other one has 2 elements. This is why the operation failed. Now, I mentioned that the library was targeted as to work with C++11. So what I did here is basically re-implementation of a nice C++20 feature. Concepts, of course. So if you have C++20 available, that would be the way to go. So I briefly show what that would look like. So in this example, I converted my types to C++20 with concepts for a small example and created such an edible concept. And then again, you would have it in the type system and get a nice error message that the two type lists here are not identical. Maybe I can move over, you can see it up here. So we directly see, okay, there's a 3-dimensional and a 2-dimensional type list, and these do not match up. So usually the saying is it's a little bit questionable whether you should make concepts for such a single operation like edible here. Debatable, I guess, but in my case, I think the operations are fairly special. So I put most of the concepts actually in or what concepts usually do in the type system. So with my matrix tag, I already know sort of what kind of matrix it is. And in that example, I would then probably use the concepts more to do the semantic check, so as little helpers, because I already know inside the type system itself what type it is. Good. Now, those were the implementation details. Now, I want to zoom out a little bit and move back to the big picture. And I want to compare what we had in the beginning, so the approach where we use the scalar type or the value type of a classical linear algebra vector to represent our vectors and matrices. This approach I call uniform matrices because it can only model matrices with uniform physical units. Here on the right-hand side is an image from the book I mentioned, George W. Hart, and that also shows the different classes of matrices that can be represented with that approach. So with the uniform matrix approach, where we only can take the scalar type or the value type of a vector and put one physical unit inside, this only gives us the gray area here of uniform square matrices or also non-square matrices and vectors. This can be represented with that approach. What I am aiming, on the other hand, with type-safe matrix is to model this second outermost blue oval, which is a much, much larger problem space. It can model all multipliable matrices. And as we will now see on that slide, even inside the gray area here, type-safe matrix is able to model the problem space much more accurately and prevents the majority of mathematically incorrect operations that are not preventable with a uniform matrix approach. To understand that, let's see what can be added and multiplied with the two approaches. So on the left-hand side, I'm showing that unit as value type approach, as I mentioned, and we'll now be looking at the addition of two vectors, A and B. Different options that we're going to look at is a point, xy point, a yz point. We have a xy displacement vector and an xy velocity vector. Now, when we look at that, we can immediately see that this approach can only prevent the operations in the last column that are marked with no, because in that case, the physical unit does not match up of the two arguments, so this can be detected, of course. But all other operations are valid, which is also natural. We don't have an annotation for the different indices or for whether this is a point or a proper vector, so there's no way that this can be prevented with this approach. All the other operations are valid with that approach. Now, if we move on to type-safe matrix and look at the same situation here, we can see that most of the table already has turned to gray. So here, for example, we cannot add 2 points, even if they have the same indices. We can also not add 2 points if they describe different indices, so xy and yz, it's not possible. What is possible, on the other hand, is to add an xy point to an xy displacement vector, or adding 2 displacement vectors with identical indices. So, yeah, all the other operations here are invalid and are prevented by the library, so most likely these are bugs, or at least the problem hasn't been properly modeled if somebody wrote it like that. As the next example, I also want to look at the multiplication of 2 matrices. So in this case, we're multiplying 2 matrices, and the different options that we're going to consider is a Jacobian matrix, we have a Jacobian transposed covariance matrix, and a vector. And as we can see, with a unit as value type approach, as I mentioned in the beginning, you can multiply any 2 physical units and get a valid result, which means if you only have a single unit in each matrix, of course, multiplying the 2 matrices is also valid, so you get a valid new physical unit, and this is the physical unit of the result. Of course, the dimensions of the matrices still have to match up, but other than that, there's no additional check, so all of these operations are valid. You could multiply 2 covariances together, or 2 vectors if the dimensions match up, so you would have to probably transpose 1 vector, but all of that is possible. Now, no surprise, if we look at what type-safe matrix does, most of the table turns to gray, and the operations are not allowed. So the only thing that we can do here is, for example, we can multiply 2 Jacobians, but not under all conditions, only, again, if the indices in the 2 matrices match up. So they have to have identical indices and describe the same things. If this is the case, then they can be multiplied. Otherwise, it would again be an invalid operation. We can multiply a Jacobian on the left-hand side with a covariance. This is what we've seen earlier. We can also multiply a Jacobian with a vector, or a Jacobian transposed with another transposed Jacobian, or a covariance with a Jacobian transposed. And all the other operations are gray here, so all of these boxes are most likely a bug waiting to happen in your code if you do something like that with a classical linear algebra library. And again, I think this is a nice example of the slogan from the beginning. If it compiles, it works. Now, until now, I've mainly talked about vectors and matrices, but of course, as I mentioned in the beginning, we also want to model transformations between different vector spaces. So the library also contains an isometry. In case you don't know that, an isometry is a transformation that contains of a rotation and a translation. So this is usually how you get from one Cartesian frame to another one. And that class has 4 template arguments. So the first one is the scalar type, double, float, whatever you want. Second one is the destination frame, so to which frame does the transform. Third one is the source frame, so from which frame is the source of the transformation, sort of. And the last one is the dimension. And similarly, also in the name, I put the source frame last. We will see in the next code example why this makes sense. So I'm putting first destination and then source. Now this code line here does an actual transformation. So we're taking on the right-hand side a position vector in odometry frame, and then we're multiplying it with a transformation that goes from odometry frame to vehicle frame, and we end up with a position in vehicle frame. Now you can probably also see why I picked the naming, because now like the identical names or types are next to each other. So we have the odometry frame on the right-hand side, then transformation from odometry to vehicle frame, and you end up with something in vehicle frame. Especially if you want to concatenate 3 or 4 together, then it's really nice. You can already see from the name that it's most likely correct. But of course, we don't have to rely on naming. All of that will be checked by the library. So if anything of that would be incorrect, like there would be a different type than what is suggested by the name, you would again get a static assertion. Now I have another question for you. Is this here, or should this be a valid operation? So we have a velocity vector in odometry frame. Then we use the transformation that goes from odometry frame to vehicle frame to end up with a velocity in vehicle frame. Should this be a valid operation or not? It should be. There was a no. Why? So you think it doesn't make sense to multiply velocities? So in general, it can make sense or can be correct, but in this case, we're having an odometry vector. So we're having, if you think of that, you have a velocity vector and you want to go to a different frame. What you have to do is you have to rotate it, of course, to get to a new coordinate frame representation. But as I mentioned, the isometry is also translating, which means it shrinks or enlarges the velocity vector. And this does not make sense if the two frames do not move with respect to each other. The velocity vector will keep its length. So it will only be rotated but not change its length, which means that this, again, is an invalid operation because velocities should not be translated. They should only be rotated. And there's also a way how this can be solved because maybe we want to transform a velocity. In that case, we would simply call the linear method of that isometry that gives us the rotational part that only rotates the velocity vector, and we end up with a velocity in the new frame. And the same thing is also true if we have displacement vectors. A displacement, so distance between 2 points, should also not change its length when you go to a different coordinate frame. It should keep its length, so you only rotate it. Only points, in the mathematical sense, are also translated because you have a new origin for that point in the new coordinate frame, so that gets a new gets new coordinates. Good. So far, we've mainly applied our slogan, if it compiles, it works, to the mathematical or physical part of the problem space. But of course, we are in C++, so there are also several or lots of bugs that can occur when you program in C++. Not sure if anybody of you has worked with linear algebra libraries before. Do you have any idea what the most common bugs are when you work with linear algebra libraries? Any ideas? Overflow, underflow, yes, that's true. But yeah, my library is not taking care of the operations at runtime. So the actual calculations are more Eigen's tasks. So that would be, so you can still fill in incorrect values, of course. That's nothing that I can prevent, especially not at compile time. But if you think maybe about borrowed ranges, if anybody's familiar with that, why is that used? Not, I'll just answer. So for me, at least in our application, or what I've seen most commonly, the bugs are, first of all, you can have aliasing. So if you're having left-hand side of your equation and right-hand side, they can alias. And if you're doing operations that don't just influence a single element, then this can lead to incorrect results. So if you have a matrix multiplication on the right-hand side and assign it to one of the matrices from the right-hand side, then you get incorrect results. That's one of the examples what can go wrong. And the second one is you can have dangling references. So you have to be a little bit familiar with what Eigen or linear algebra libraries do to know that. They usually return matrix expressions. So when you say, please calculate A plus B, it's not actually calculating that. It's simply creating an expression object that describes how this can be calculated if it's assigned to something. And this can, like, usually stores the arguments by reference if you have a proper vector matrix for efficiency regions. And this can lead to dangling references. I will explain on the next slide how this can happen, and we will also see how this can be prevented completely. So as I mentioned, with Eigen, it uses expression templates. So let's look at a really small example here of Eigen Code. So we have a method calculate offset that returns an Eigen three-dimensional vector by value. And then we also have a pre-existing three-dimensional vector, vector A. Now I can write code like this here. So we're adding vector A to the result of calculate offset. And then we're calculating the norm method to get the length of the vector. And we assign that to a double. It's completely valid Eigen code. Everything is fine. But now I can change one small thing that makes this invalid code and accesses. Oh, sorry, I shouldn't tell what it does. So first of all, let's see how I can break it. So when I pull that apart, and first create an auto variable sum that stores the sum of vector A plus, so the result of the addition of vector A plus the result of calculate offset. And then on the next code line, I calculate the norm method. Then we have a bug here. This is exactly what I mentioned earlier. You might think that sum is now a vector that stores the result. But as I explained, Eigen only creates an expression object that describes how this can be evaluated if it would be necessary. And for efficiency reasons, the arguments to such an expression are stored by reference if the argument is a proper vector matrix. Meaning we're storing a reference here to the result of calculate offset, which is a temporary, an R value, meaning this is only valid on that code line. If we go to the next code line, you're accessing something that's no longer existing. So this is undefined behavior. You're accessing a dangling reference. And if you're lucky, the code crashes. You can fix it. If you're unlucky, it silently works and gives incorrect results or breaks at some later point. And the exact same thing would also happen if we capture that result by reference. So if we use an auto reference here to capture that sum or the result of the sum operation, we would have the exact same problem. Now the question is, can we prevent this, or how can this be prevented? So we might think maybe we just forbid the creation of any matrix expressions, but these are fairly important for an efficient implementation of the libraries usually, so it's not possible to completely forbid them, but we can forbid calling any methods on L values. So if we have an L value matrix expression, we can forbid that the user calls any method on that, and this prevents all of these misusages without imposing a lot of restrictions on the user. I will show how this can be done. So we're again looking at the addition operator that we've seen earlier in our matrix base class, and we now need two overloads of that method. The first one has an L value reference qualifier, meaning it will be executed when we do the operation on L values, so on named variables. And the second one will be executed on R values if we're doing that on temporaries. Question, yes? Why a constant R value reference? Because it's not the plus equals operator, it's the addition that returns a new vector that adds the two, so we're not modifying the argument, the class in which we're operating. Sorry? Yeah. Yeah, the first one is the L value reference. Good, and now what we have to do in that L value reference method is that we check that we're not in a matrix expression. That's a simple static assert helper method that checks that we're not in a matrix expression. Otherwise, this thing would fire a static assertion and alert the user of the problem. And then, in an addition, of course, we also have the second argument. So the other argument here, and we again have to verify that this other argument is not an L value matrix expression. If that would be the case, again, a static assertion is fired. And last but not least, we are forwarding to the underlying linear algebra library for the actual calculations, which means we're just calling the addition operator of the underlying eigentype in this example. Interesting thing to note here on the bottom, we have to do a std move under this pointer in the R value reference qualified version, because otherwise we would end up in the L value qualified version of other methods that we're calling from that class. This is important. There's also a new proposal, or it's actually made its way into C++23 using this. That would simplify this. I could write that in one method with that new proposal, so it's fairly nice. If you're interested in the details, read it up. Jason, yeah?
I'm sorry, I feel like I must have missed something, but related back to the question of why is that a const R value reference, aren't you moving on a const this reference on that line, which wouldn't do anything?
Yeah, it doesn't really do anything, but as I have always these two overloads, L value and R value reference qualified versions, I want to end up in the const R value qualified version of that underlying method. So yeah, It's not for efficiency or anything. I mean, in our application, we anyways not using dynamic memory. So for me, these value categories are more, yeah, I'm using it for exactly that. So it doesn't make it more efficient or anything if you don't have dynamic memory.
Just to choose the overload.
Yeah, I'm choosing the overload with that, exactly. And this, again, is a nice example of if it compiles, it works. So I'm trying to prevent all the operations that can be invalid or can lead to bugs. I also have a prevention for aliasing, but due to time constraints, I can't discuss that today. If you want to know details, I have a 90-minute talk from CppNorth this year. You can watch that there. I'm explaining a little bit more of the details. So that already gets me close to the end. What have we achieved so far? So as we've seen, we've achieved full support for physical units in all vectors and matrices. Furthermore, we've also achieved expressive and enforced names for all vectors and matrix entries, so the user always has to mention what he's accessing. And we have a full protection against out-of-bounds access in vectors and matrices at compile time. Furthermore, we've seen that we can come up with a proper taxonomy or domain model for all linear algebra types. So we've seen that there are covariance matrices, Jacobians, row column vectors, and a lot more. And I think it also makes a lot of sense to distinguish that so that you have a sort of real semantic description of what you're doing, what operations you're executing. And as we've seen, we've introduced a compatibility check for all index structs and matrix types for all linear algebra operations. We also have a built-in coordinate frame tag-in, so we can tag, okay, this is a vector in coordinate frame A or a vector in coordinate frame B. And we've seen how we can prevent the dangling reference bugs that can occur when you're using Eigen. And also, as I mentioned, the aliasing can also be prevented. Check out my other talks if you're interested in that. And last but not least, we've seen how we can come as close to the ultimate goal in library interface design as possible, which is, if it compiles, it works. Wait, here. Now we have it. Okay, here. Too quick. So I want to mention we at Bosch in Germany are hiring. We're also hiring in ETAS in York. So please check out the job listings if we're interested. There's also something in Plymouth in the US if you would be interested in driver assistance that's closer to here. And then all that remains to be said from my side is to thank you for listening. I'm now looking forward to your questions.
What's the relationship with that solution you proposed and two proposals that exist right now, which is the unit proposal and the linear algebra proposal? And do they... Oh, okay. And do they address the needs that you just presented?
Okay.
And how do you think the design of those proposals should change to address your?
Well, the question was how that relates to the physical units and the linear algebra proposals that are out now for C++. Well, I don't have a lot of requirements for that, so I'm mainly using them as a backend sort of. So I need an underlying physical units library, first of all. We have an in-house one since 15 years now in our company, but I also have a binding for Matrices library, so I can switch. And I do have a binding for Eigen, for Blaze as a linear algebra library, and also for our in-house library. And all of that works. So just this week, we replaced our code to no longer use Eigen, but use our in-house library instead. And this is sort of one switch if you've written everything correctly. Of course, there are also ways how you can access the underlying type. So if you've done that, then these things have to be changed. But otherwise, it's a simple switch, and you can switch between different linear algebra libraries. So I don't have that many requirements. Maybe for the linear algebra proposal, I think they adapted it a little bit, that they distinguish between row and column vectors. This is something that I find fairly useful, and I'm also using a lot. And what is important for me that I have a uniform way how you can access vectors and matrices. So it should have the call operator, and you should be able to also call a vector with 2 arguments for that call operator, because that makes my code so much easier. Otherwise, I end up having to write 5 or 10 overloads for some methods. So if you treat vectors and matrices uniformly in the underlying library, this is really helpful for me. But otherwise, I don't have many requirements. Yeah.
Thank you.
Hi. I like how you represent the matrix with the 2 type list. I just have a question about how you give access to each individual cell from the matrix so that you can get the row 3 and the column 4. So
the question is how I can give access to the value of the row
individually.
This can be done with the methods that I've shown, the add and coefficient SI,
okay.
Or did you have a different thing in mind?
I didn't see the add method. Sorry.
Yeah, so add gives you just the scalar, so double or float. As I mentioned, that's not that type safe, so it should be avoided. And the coefficient SI or coef SI method gives you a physical unit. And there's also the entry method that sort of gives you one entry packed in a one-by-one type-safe matrix. So it's actually a small matrix by itself, what you have there. And that can then be used to assign it to an entry in another matrix, for example.
Okay. Thank you.
Good. One more question, yes?
Hey, thanks, awesome presentation. It's nice to see another approach to using linear algebra and matrices and simulations and positions and all that. So the question is, how efficient is this in the resulting code on the C++? How is there a performance impact on this?
So the question is there a performance impact? So first of all, maybe I should mention compile times. It's a template library. So there's a small, noticeable compile time overhead. So 20 to 30%, I think, is what the compile times goes up. That's what I measured. And regarding runtime, I also did benchmarks, like benchmarking plain eigen with my library wrapping eigen. And the overhead is, I don't know, 1 to 2% in some cases, but it's not clear that eigen is always more efficient. Sometimes it's also the other way around, actually. I think sometimes what I did here might even help, because I'm preventing a lot of alias situations. Because if you go to a different frame, you have a completely new type. So it's more difficult to assign to the same variable from the right-hand side. And that might actually help in some cases for the optimizer. But yeah, I think it's almost zero overhead or zero overhead. I haven't noticed any like case where it really causes significant overhead. So it's really a thin wrapper and seems to work with the optimizers these days. Good, I think that was the last question. Then thanks again, everyone, for coming.